Antarctica is the coldest place on Earth. At Russia's Vostok station back in 1983, the thermometer dropped to about minus 128 degrees Fahrenheit, a number that just hurts to read. At that temperature, a deep breath damages your lung, steel turns as brittle as glass, and a cup of boiling water flung into the air falls back down as a flurry of ice crystals before it ever hits the ground. An ice inferno, right? Now look up. Not far, only about 60 miles straight overhead. The length of a good road trip stood on its end. This is where space begins, and that is where our record-breaking cold suddenly feels almost cozy. Next to deep space, Antarctica is an oven. Out there, the thermometer plunges to roughly minus 455 degrees Fahrenheit, a hair away from absolute zero, the lowest temperature the universe will allow. And this is the part that should not make sense. Space is not a dark, empty room. It's flooded in every direction by the light of the sun, a star's whose surface burns near 10,000 degrees Fahrenheit. And not only our sun, but billions upon billions of others, all blasting heat into the cosmos for billions of years. So why is space not boiling? Why can the vacuum not hold on to all that heat? By the end of this, you will understand why you could survive longer in the frozen heart of a glacier than in the cosmic vacuum. And the reason is not the one almost everyone assumes. The cold, it turns out, is barely the problem at all. Quick thing before we go on. If you like the universe explained without the jargon, subscribe and tap the bell so the daily videos actually reach you. Now to the mystery. Let's start at the very bottom with the question hiding underneath everything else. What exactly is temperature? We throw the word around every single day, very casually, but we rarely stop to ask what we are actually measuring. And this is the first knot to untie, the most important one of all. Temperature, when you get right down to it, is movement. It is agitation. Take anything, the air in this room, the water in a glass, the iron of a gate, and zoom inside all the way down to the atoms and molecules it is made of. They're never still. They vibrate, zip around, slam into each other, and bounce away like a frenzied crowd in a stadium. The more wildly the particles move, the hotter the thing is. Catch them racing like mad and you have hot stuff. When they slow down, settle and drag along lazily, that is the cold stuff. Absolute zero, that famous minus 460 degrees Fahrenheit, is simply the point where they stop completely. The full stop, the absolute silence of motion. So temperature is not a substance, not some fluid that fills things up. It is the frenzy of the particles, a measure of how hard they are dancing. And now that you know that, brace yourself, because the first real twist is the one that turns everything on its head. If temperature is the movement of particles, what happens in a place where there are no particles? Because that is exactly what space is. Empty. The most extreme vacuum you can imagine. In a single cubic yard of deep space, a box about a yard on each side, you're lucky to find one atom. One. For comparison, that same box of air here on Earth holds a number with 25 zeros after it, something like 27 million billion atoms. So the question, what is the temperature of space, becomes almost meaningless. It's like asking what mood an empty room is in. Moods belong to people, not to rooms. And temperature, the real kind, made of particles in motion, belongs to matter, not to the void. Space, strictly speaking, is not cold. Space is empty. Those are two profoundly different things, even if in everyday life we blur them together constantly. But then you'll fairly ask, why does that thermometer planted out in space still read deep below zero? If the void has no temperature, what on earth is it measuring? Good question, and the answer takes us straight to the heart of it. To get there, we have to talk exactly how heat moves from one place to another. Heat is a great traveler, and it has exactly 3 ways to set off on a journey. Only 3. And the whole secret of this mystery is that in space, 2 of those 3 are simply forbidden, switched off out of order. The first is conduction, the most direct of all. It is heat passing by contact. Touch a scorching pot and you get burned as the heat leaps straight from the metal into your hand. It works like a relay. a chain of particles knocking into one another. The hot, wildly agitated ones slam into their calmer neighborhoods and set them moving, which shove the next ones along, and so on. A contagion of frenzy spreading from particle to particle. But to run that relay, you need particles, a great many of them, packed tight and able to touch. In the empty vacuum of space, there is no one to pass the ball to. The chain snaps at the very first link, since a single link does not make a chain. Conduction up there is essentially zeroed out. The second way is convection, the one that heats your home. It's heat carried by a moving fluid. Warm air is lighter, so it rises. Cold air is heavier, so it sinks. That sets up the great merry-go-round that mixes and spreads heat through a room. It's how a radiator warms even the farthest corner, and how pasta cooks in boiling water. But convection needs one fundamental thing to exist: a fluid. Air, water, something that can flow and circulate. In the vacuum of space, there is no fluid to rise or fall. No air, no currents, no merry-go-round. Convection up there is switched off as well. And that leaves a stark result. Two of the three couriers of heat, conduction and convection, the only two that work by contact and depend on matter, cannot do their job in space. The delivery drivers are missing, and so is the very matter they would travel on. But the third way remains, and the third one is special because it is the only one that needs nothing and no one in order to travel. It's called radiation. Radiation is heat moving in the form of light, more precisely, infrared, the kind you cannot see but can feel. The same warmth that reaches you when a hand comes near a stove, or when the summer sun warms your face even though the surrounding air stays cool. Every object, you included, right now is constantly giving off this invisible light, radiating a little of its own heat in every direction. And the remarkable thing about radiation is exactly this: it needs no medium to cross, no particles, no air, nothing at all. It sails through the vacuum perfectly happily. That is how the sun's light and heat reach us in the first place, crossing 93 million miles of pure vacuum to arrive right on time and warm our skin. So let's pull the threads together. In space, conduction and convection are out of the game. Only radiation survives, and here at last the riddle of the thermometer comes apart. That thermometer, abandoned in deep space, far from the sun and the stars, cannot trade heat by contact with nothing out there to touch. The one thing it can do is radiate, spitting its own heat out as infrared light and sending that off to wander the cosmos. Meanwhile, from outside, the device gets nearly nothing back, since no nearby star is there to warm it. The reading keeps falling, heat bleeding away, and almost nothing returns. So it cools, dropping and would settle at exactly absolute zero, if not for one faint, feeble glow that fills the entire universe. The leftover echo of the Big Bang, a fossil radiation soaking every corner of the cosmos. That dim background hum keeps the thermometer pinned not quite at zero, but a sliver above it, at about 2.7 degrees over absolute zero, the same deep reading we started with. And that is the real measurement, not the temperature of the void, which does not exist, but the temperature any lonely object left out there shedding its own heat with nothing to give back finally drifts down to. Now, with every piece on the table, let's return to the promise from the start, the thing that sounded like a lie. That in space, the real danger is not the cold, it is the heat. Think of yourself as an astronaut outside the spacecraft, sealed in a suit. The body is a little furnace. Every cell is burning, working, producing heat without pause. On Earth, nobody notices this, since we shed that heat constantly and effortlessly. Cool air brushing the skin carries it away by contact. Evaporating sweat cools the body down. Every breath out dumps a little of the excess. 3 exhaust channels always open, and the body is brilliant at getting rid of surplus heat. But up there in the vacuum, those channels slam shut all at once. No cool air touches you to carry the heat off, so conduction is gone. No breeze, no current to run the merry-go-round, so convection is gone. You're left with a single exhaust, just one, to radiate, to spit your heat out as infrared light, slowly, the only route left. And radiation on its own is painfully slow next to the work 3 of them were doing back on Earth. Your body keeps making heat at full tilt, but it can barely let it go. So the heat begins to pile up inside you like a car sealed under the August sun. You don't freeze. If anything, you risk cooking in your own warmth. That's why, and almost no one pictures this, spacesuits are not built to warm astronauts up. They're built to cool them down. Beneath the outer layers, a spacewalk suit holds a dense web of thin tubes, around 300 feet of them, with chilled water running through against the skin. A cooling system that snakes the length of the whole body to pull away the heat the astronaut can no longer shed alone. The number one enemy out there, in the vacuum near absolute zero, is the risk of stewing in your own juices. It sounds like a paradox, and yet it is the perfectly logical consequence of everything we have said. Space is cold not because it tears the heat out of you. Just the opposite. The vacuum has a terribly hard time taking heat away at all, since it lacks the tools, lacks the very particles of contact. Space runs cold only in the sense that an object left out there alone, far from any star, will over long ages empty itself of heat by radiating away and drift toward absolute zero. But that slow drift is the whole point. The process is patient, never the instant icy grip we picture. So the question we started with, why space is so cold when the sun and billions of stars are so hot, dissolves into an answer that flips our intuition upside down. Space is not cold. Space is empty. All that stellar heat, that tide of radiation crossing it in every direction, is just light passing through. It streaks across the vacuum without warming a thing, since almost no matter is there to catch the light and start vibrating. The heat arrives only when it strikes something solid, a planet, a rock, the skin of an astronaut, the glass of a thermometer. Only then and only there does light turn back into heat. The void, quite simply, is not invited to the party. That is why you really could last longer in the frozen heart of an Antarctic glacier than in the cosmic vacuum. Space does not freeze you faster than the ice, far from it. But out there, there's no air to breathe, no pressure to hold your body together, and the heat you make has nowhere to go. The cold, that spine-chilling reading near absolute zero, is just about the least of your worries. The universe is a place full of boundless fires, billions of stars that have blazed for billions of years, and still between one fire and the next stretches an immense, silent void whose fires cannot fill. Not that the heat is missing, but that what is missing is the matter on which that heat could, at last, come to rest. If all this rewired how you think about hot and cold, you will want the original deep dive that kicked it all off. We unpack the whole paradox in our viral video on why space is so cold when the sun and billions of stars are so hot. Go watch that one next.